Welcome back to The Historian. Tonight, we look at the lunar enigma, chronicles of the forgotten observatories of the moon. Our journey into lunar curiosity begins thousands of years ago, as ancient civilizations first turned their eyes toward the silvery beacon hanging gently in the night sky. The allure of the moon has beckoned humans since prehistoric times, sparking imagination and the seeds of scientific inquiry. The ancient Sumerians, around 3500 BC, were among the very first to leave records showing their fascination with the moon. They observed its changing phases and its regular path across the heavens. Using simple tools and keen observation, these early astronomers laid the groundwork for what would become a complex understanding of celestial movements. In ancient Babylonia, around 1000 BC, lunar observations became even more sophisticated. They developed a calendar based on lunar cycles, dividing the year into 12 months corresponding to the cycles. Their priests, deeply invested in astrology, meticulously recorded lunar eclipses. These observations were not just for keeping track of time, but also for religious purposes, as they believed the movements of the moon influenced events on Earth. Egyptians, contemporaries of those ancient Babylonians, also valued lunar observation. However, they preferred aligning their calendars with the sun and the flooding cycles of the Nile. Yet, their monuments reveal their respect for celestial bodies. The Great Pyramid of Giza, meticulously aligned with the cardinal points, shows us how these structures also bore witness to their knowledge of the heavens, even if their primary focus lay more upon solar observations. Ancient Greece offers us a more distinguished record, where philosophers began to step into the realm of scientific reasoning. Around 400 BC, the philosopher Anaxagoras speculated that the moon was a massive rock reflecting the sun's light, challenging the mythological narratives of his time. A century later, Aristarchus suggested the revolutionary idea that the Earth orbited the sun, and that the moon's phases resulted from its position relative to the sun and Earth. By the time of Hipparchus, in the 2nd century BC, lunar observations had reached new heights. Known as one of the greatest ancient astronomers, Hipparchus compiled the first comprehensive star catalog. He also improved predictions of solar and lunar eclipses using trigonometric methods, an impressive feat that set the stage for future astronomical inquiry. The traditional tools were simple: gnomons, which were sticks or poles used to measure the sun's angle and shadows, and later, more advanced instruments like the astrolabe. These instruments allowed Babylonian and Greek astronomers to create more accurate predictions of lunar eclipses and understand the moon's nuances. Further east, Chinese astronomers in the Han Dynasty also made significant contributions to our understanding of lunar phenomena. They diligently cataloged celestial events, with records of lunar eclipses dating back to the 6th century BC. The Han astronomers recorded their lunar observations with precision, contributing richly to the annals of astronomical data that were passed down through generations. Much of our knowledge about these early pursuits comes from texts painstakingly created on clay tablets, papyrus, and even inscribed on ancient stone structures. Each of these ancient cultures brought their unique understanding and methodologies to the study of the moon, forming a foundation for later astronomers across the world. As we drift further into this celestial narrative, the story of lunar observation will evolve dramatically with the invention of the telescope. However, let us linger for a while on these ancient observatories of the mind and stone. The imagination, driven by curiosity about the moon, started its journey not with the sophisticated equipment we have today, but with the simple, honest awe at the moon's presence. The moon has always been more than just a distant celestial body. Each ancient observer carried forward a legacy of celestial understanding, setting the stage for future generations who would reach out, not just with eyes and minds, but eventually with technology. As the stars consistently flow through the sky, so too do ideas evolve, leading to the worlds unlocked by those daring to look beyond. This pursuit, driven by the earliest gazers, is one we continue to chase even today, as modern observatories reach ever further into space. In the quiet hours of ancient evenings, when the world settled into stillness and the sky unveiled its celestial array, early civilizations began the fascinating endeavor of mapping the moon. Long before the invention of the telescope, people were inspired by sheer wonder and a longing to navigate the mysteries above. These lunar cartographers embarked on their journeys using keen eyes and nascent tools. The first recorded attempts at mapping the moon can be traced back to classical Greece, particularly with the work of Ptolemy. Geographer and astronomer Claudius Ptolemy, in the 2nd century AD, began composing influential texts that would guide lunar, planetary, and star studies for many centuries. Although later generations would refine lunar maps, Ptolemy's initial compilations were essential stepping stones in the vast river of scientific exploration. Across cultures, the moon's surface intrigued and baffled viewers. In this era, the moon was perceived not simply as a luminous ball but as a surface holding more secrets. Yet, how to record these secrets? Without modern technology, the early astronomers relied on detailed observations and artistic interpretations, blending observation with imagination. Moving westward to medieval Europe, Islamic scholars emerged as key figures in lunar cartography. Their culture, devoted to learning and scholarship, encouraged detailed studies of astronomy. By the 9th and 10th centuries, scholars like al-Battani and al-Biruni made exceptional strides. They meticulously observed celestial bodies, again without the benefits of telescopic aids, recording observations with major impact on both Islamic and Western astronomy. Al-Battani, an astronomer from what is now modern-day Turkey, compiled incisive notes about the moon's movements and phases. His works, written in Arabic and later translated into Latin, crossed the cultural chasm that divided East and West during medieval times, contributing significantly to Europe's own astronomical renaissance. His refinement of Ptolemy's geocentric model helped future scientists understand the dynamics of celestial orbits. The tools of the time were rudimentary yet effective. The astrolabe, among the most revered, was already known by Greek and Islamic astronomers. Using this, dedicated observers could measure the altitude of stars and celestial objects above the horizon, allowing them to estimate the moon's position accurately. It was a combination of observation and calculation, a precursor to modern mapping techniques. To the east, China's Tang dynasty also showcased an impressive perspective on lunar studies. The famous Dunhuang star chart, dating roughly to the 7th or 8th century AD, represents one of the oldest known complete sky maps. While primarily focused on the stars, such achievements underscored the era's precision and dedication to understanding the entire celestial sphere, including the moon. From Greece to the Islamic Golden Age, and further to China, each civilization contributed uniquely to the intricate task of lunar cartography. Though their maps were not as complete as modern maps, the value lay in their pioneering spirit, sharing a synchronized view that the moon was a crucial fixture influencing life and understanding on Earth. However, the moon's true mapping would take another giant leap with the invention of the telescope in the early 1600s, which would dramatically deepen humanity's gaze into its cratered surface. The groundwork, however, was laid patiently over centuries, with each generation gazing up and passing down their understandings of our celestial companion. In the dawn of the 17th century, the ever-curious gaze of humanity turned not just upwards, but through a new lens, ushering in the age of the telescope. This period marked the transition from unaided vision to enhanced clarity of the cosmos, where the moon became not just a distant glow, but a realm within visual reach. The inception of the telescope opened an era of profound lunar revelation. Early telescopic advancements rested on the shoulders of pioneers like Hans Lippershey, who in 1608 was credited with the earliest construction of what could be called a telescope. Although rudimentary, these initial devices magnified the sky's wonders, setting the stage for more astronomical discoveries. It was, however, Galileo Galilei who transformed telescopic technology into a new chapter for lunar study. In 1609, Galileo crafted his own telescope, improving significantly upon initial designs. With this instrument, he peered at the moon, revealing a rough and cratered surface. Prior to this, many had envisioned the moon as a perfect sphere, a heavenly body without blemish. His observations debunked these notions, presenting to the world a celestial body rich in textures and mystery. In March 1610, Galileo published Sidereus Nuncius, or Starry Messenger, detailing his discoveries. His meticulous sketches offered the first detailed depiction of the lunar surface, noting mountains and valleys, all previously invisible to the naked eye. Through Galileo's groundwork, the celestial perspective shifted profoundly, spurring further astronomical exploration. If one found peace in these archives of knowledge, remember to subscribe to join us on the next journey. Galileo's work also inspired other celestial cartographers of his time, such as Johannes Kepler, who not only verified but expanded upon these lunar studies. Meanwhile, on the parallel track of progress in England, Thomas Harriot independently observed the moon and crafted his own maps of the lunar features. Harriot began his observations even before Galileo's famous journey through the stars, but his contributions remained less known in his time. These new lenses acted as windows into the cosmos that allowed our ancestors to piece together more accurate maps, placing the moon's mountains, craters, and valleys onto paper with astonishing accuracy. The telescope, now an astronomer's staple, was evolving rapidly. As the tools became more sophisticated, so too did our understanding of the moon's superficial mysteries. As Europe was diving deeper into the night sky, other parts of the world began to recognize the power of these advancements as well. The spread of telescopic technology sped up communication among the scientific communities, fostering an unprecedented exchange of knowledge and discoveries. Franco Borgari, a Venetian astronomer, painstakingly documented the lunar physiognomy, creating the first recognizable and detailed maps of the moon. His approach involved careful sectional sketches, emphasizing the cratered landscapes Galileo had uncovered. Each astronomer stood on his predecessor's shoulders, navigating humanity's deepening interest in lunar mysteries. The collaborative spirit across borders, propagating through Europe, laid the groundwork for future observations. These telescopic eyes, now gazing at a desolate sphere, reignited age-old imaginations and inspirations for travelers of the heavenly trails. Moving into the late 17th century, advancements continued, with figures like Giovanni Cassini and Philippe de la Hire making more exact observations and producing thoroughly detailed lunar maps based on telescopic studies. The contributions during this period were vital in building the growing archive of moon knowledge. The emergence of the telescope at the dawn of the 17th century marked a pivotal point in humanity's pursuit of understanding the cosmos. Each night spent observing, and each map drawn revealed not just the lunar surface, but also humanity's unyielding spirit to grasp the unknown. As the stars drift across the horizon and moonlit tales emerge, humanity's quest to understand its place among the celestial tapestry continues, echoing the dreams of those early gazers who bravely looked beyond our world. In the quiet development of early modern science, attention turned to constructing the physical spaces where lunar observation could thrive. These structures, known as observatories, became the focal points where the age-old fascination with the moon met the dawn of systematic study. One of the first architectural feats in astronomy was Tycho Brahe's Uraniborg, built in the late 16th century on the Danish island of Hven. While Tycho did not use a telescope, his work predated its invention. He designed his observatory to allow precise measurements of celestial phenomena. Uraniborg was both a palace and a scientific workshop, its walls lined with the finest instruments of its day. This combination of architecture and advanced tools propelled Tycho to new heights in data accuracy, contributing critical observational records that would benefit astronomers like Johannes Kepler. As the telescope became increasingly central to astronomy, the design of observatories adapted to these technological advances. The 17th century saw the construction of the Paris Observatory in 1667, a significant milestone in the history of astronomical architecture. This building was the first designed specifically for astronomical purposes. The aims of such observatories were to create environments where telescopes could operate free from as much atmospheric distortion as possible. Architects and astronomers began to choose high-elevation sites to minimize interference from weather and urban pollution. Another pivotal step in observatory architecture was the Greenwich Observatory in England, completed in 1676. It was strategically placed on a hilltop, taking advantage of clear sky views. Sir Christopher Wren, the renowned architect, designed the building, ensuring it included a large room for a massive sextant and windows carefully positioned for observations. These early structures had domes or other movable ceilings that would open to the sky, ensuring telescopes had unobstructed views. This became a key feature and remains so in modern observatories. In these observatories, scientists studied lunar phases more precisely, focusing on the movement of shadows across the moon's surface to learn about its topography. In Italy, another important observatory added to lunar studies was the Collegio Romano Observatory, affiliated with the Roman Catholic Church. It was here that astronomers like Jesuit priest Giovanni Battista Riccioli mapped the moon extensively. His detailed lunar map, produced in 1651, introduced many familiar names for moon features, such as Sea of Tranquility. The construction of these dedicated observatories was not haphazard, but rather planned with great meticulousness to aid specific goals. Accurate timing, detailed mapping, and reliable records of lunar and other celestial events. Much of this architecture was a blend of function and style, serving both scientific and spiritual pursuits, often reflecting the wealth and influence of their patrons. This era witnessed the introduction of powerful, larger telescopes placed in more stable housing that could pivot across the night sky. Observatories became emblematic not merely of human curiosity, but also of organizational science and the quest for exactitude in measuring celestial phenomena. These buildings and the activities within them symbolized a fusion of ancient observational techniques with new technologies. The creation of observatories marked significant collaborations across countries and cultures. Their designs pushed the boundaries of engineering and architecture, as scholars and builders worked together to create spaces that would support the heavy and precise instruments needed for astronomical progress. This forged a global alliance among the scientific community. As the night faded into the glow of morning, these observatories continued their silent watch, peering into the mysteries of the moon. They symbolized a quest that respected tradition, yet reached eagerly toward the future. As the wave of the new scientific revolution swept onward, these structures set the stage for an era of discovery, revealing more about our moon and the cosmos beyond. This architectural legacy laid the groundwork for understanding the broader universe, and as the twilight of one era rolled into the dawn of another, it was clear that the spirit of exploration would only deepen its celestial reach. As the 18th century unfolded, societies worldwide embarked on constructing observatories, igniting an era that propelled lunar research into new realms. Europe stood prominently at the heart of this movement, where academic and governmental institutions recognized the value in refining their celestial understandings. The evolution of these observatories was not simply confined to Europe, for the allure of the moon had become a universal pursuit. In Russia, the Pulkovo Observatory was established near St. Petersburg in 1839. Known as the astronomical capital of the world at its inception, Pulkovo was the brainchild of Friedrich Georg Wilhelm von Struve, an esteemed astronomer dedicated to precise astronomical observations. This site focused intensely on cataloging stars and other celestial bodies, including detailed studies of the moon. Through its rigorous endeavors, Pulkovo played a substantial role in advancing lunar research and contributed greatly to the understanding of the celestial mechanics of its time. Across the Atlantic, the United States was also constructing observatories, with the Naval Observatory in Washington, D.C., opening its domes in 1844. Originally designed to support naval navigation by providing precise timekeeping, it quickly became a center for lunar observations. Here, the central task involved improving lunar distance measurements to aid mariners in determining their longitude while at sea. Over time, it became a hub for astronomical innovation. In the Southern Hemisphere, Australia joined the global tapestry of astronomical efforts with the establishment of the Sydney Observatory in 1858. This site was strategically perched on Observatory Hill to maximize clear sky visibility. Initially, it served dual purposes of timekeeping and weather observation, but developed into a significant site for lunar studies. Its construction was a testament to the spread of astronomical interest reaching new latitudes and geographies. Meanwhile, Europe continued to refine its observatory infrastructure. The Royal Observatory in Edinburgh, Scotland, opened in 1896, an iconic center for lunar and planetary research. This observatory played a crucial role in international projects that required meticulous data compilation over extended periods. Its clear night skies and advanced equipment made it an ideal location for detailed lunar observations. Observatories in this global push were more than brick and mortar. They were symbolic of the human spirit's unyielding drive to explore and understand the universe. They represented a collective human endeavor, pooling resources, expertise, and innovation to unlock the secrets held by the moon. These facilities were equipped with modern instruments, like increasingly powerful telescopes and sophisticated chronometers, which allowed for unprecedented precision in celestial observations. In these global hubs, astronomers from varied backgrounds collaborated, crossing cultural and national boundaries. The observatories facilitated international conferences and collaborations, birthing a fraternity of scholars dedicated to lunar exploration. These gatherings fostered a spirit of shared knowledge and innovation, transcending political differences in the pursuit of scientific advancement. The astronomical societies emerging during this time facilitated exchange among professionals and enthusiasts alike. Publications grew more widespread, sharing nuanced observations and innovations that fueled a shared human pursuit of knowledge. They served as conduits, spreading new ideas and propelling forward the intricacies of lunar research. These observatory expansions reflected global shifts toward embracing scientific exploration. As observation techniques advanced, so too did the interpretations of lunar landscapes. The moon's rugged terrain became a subject not just of intrigue, but of thorough scientific inquiry. Detailed maps emerged, bearing names for craters, seas, and mountains, offering new perspectives on the lunar surface. Amidst these explorations, the moon carried a deeper significance. It was a unifying symbol in a rapidly changing world, anchored in ancient curiosity, yet burgeoning into a new era informed by groundbreaking discoveries. As understanding deepened, the moon's story evolved from myth and imagination to science-backed reality. The observatory boom encapsulated a period where the global scientific endeavor was not just about investigation. It was a beacon of civilization's aspirations, uniting disparate worlds under the common pursuit of celestial discovery. The worldwide network of observatories harnessed the collaborative spirit of the Earth's multitudes, bridging distances and cultures through their unyielding gaze into the night sky, signaling future expeditions beyond even the moon's grasp. In the blossoming period of the 17th and 18th centuries, the study of the moon reached new pinnacles. Key figures emerged, whose contributions not only advanced lunar knowledge, but also laid the foundational stones that modern lunar science stands upon. Among these prominent individuals was Johannes Hevelius, a wealthy Polish brewer and an avid astronomer, who devoted his life to the study of the moon and stars. Hevelius, working in the bustling port of Danzig, was renowned for his meticulous lunar observations. Although primarily self-taught, his skills in astronomy became increasingly sophisticated. In 1647, he published Selenographia, a comprehensive atlas of the moon that detailed its surface. This work included some of the most accurate maps of its time, with detailed depictions of the various lunar seas, mountains, and other geographical features. Hevelius' commitment was unwavering. His maps remained the reference for lunar surface study for decades to come. Far to the west, another figure was making strides in lunar observation. Giovanni Domenico Cassini, an Italian-born astronomer who spent a significant portion of his career in France, contributed substantially to our understanding of the moon and its movement. In the latter half of the 17th century, as the director of the Paris Observatory, Cassini calculated the lunar parallax accurately, which helped in determining the moon's distance from Earth. While he is often celebrated for his observations of Saturn, his work with lunar phases and parallax significantly influenced the study of the moon. Cassini also competed with other astronomers of his day to hone the precision of lunar observations. His observations enabled ever more accurate models of the lunar orbit, enriching the catalog of data astronomers relied upon for navigation and calibration of timekeeping instruments. This data was invaluable in a time when seafarers navigated the globe using celestial bodies. In England, the methodical gaze of John Flamsteed illuminated the lunar subject. Appointed as the first Astronomer Royal in 1675, Flamsteed played a crucial role in lunar cartography. By meticulously observing the night sky from the Royal Greenwich Observatory, he compiled extensive star maps and lunar observations. His work helped refine celestial calculations used by navigators and would later aid Isaac Newton in his work on gravity. Flamsteed's endeavors were part of a broader movement towards systematic observations and records. His star catalog, published posthumously, laid the groundwork for future astral discoveries by providing a reliable reference point for astronomers across Europe. While these men made significant contributions, others such as Cassini's counterpart in England, Edmund Halley, also engaged in exploring lunar phenomena. Halley, intrigued by eclipses and their prediction, utilized his understanding of lunar motion to improve the methods for predicting the timing and duration of these celestial events. His work intertwined with gravitational theories and influenced how the moon's gravitational pull impacts Earth, enriching the understanding of tidal forces. The collective efforts of these astronomers fostered an era where lunar observation became increasingly precise and scientific. Their work was indispensable as it transitioned humanity's understanding of the moon from mystical speculation to a real, celestial body governed by physical laws. This period signaled an awakening in lunar science, which aligned with broader strides in astronomy across the globe. The achievements of Hevelius, Cassini, Flamsteed, and Halley epitomized a shift towards structured scientific inquiry. With eyes turned skyward, the moon's face was charted in exquisite detail. The legacy of their work paved the way for even grander celestial explorations, stitching together a tapestry of knowledge that continues to shape our understanding of the moon today. As the moon glows softly in the night sky, we remember these pioneers who gazed upwards and brought the stars and moon into a closer embrace with our everyday lives. In the quiet glow of the 17th century, astronomical exploration was alive with earnest minds and diligent hands, as humanity pressed into the heart of its golden age of celestial discovery. Within humble observatories under expansive skies, a community of astronomers emerged, shaped by their nightly routines and fueled by unyielding curiosity about the moon. Each day began with simple preparations. As the sun sank beyond the horizon, Astronomers peered into meticulously polished telescopes, their breath visible in the cool air. These telescopes, crafted with care and constantly refined, extended their reach into the heavens, revealing complex lunar landscapes previously hidden to the naked eye. The routine was unwavering yet filled with quiet adventure. Astronomers like Johann Hevelius and Giovanni Cassini spent countless hours recording detailed notes. Their observations of rugged lunar surfaces were intense, aiming to understand the orbit and geographical nuances of the moon. They studied lunar maps painstakingly, marking mountains, seas, and craters in volumes that grew thicker with each night's discoveries. Beyond the maps, the golden-aged routines involved precise calculations and artistic renderings. Hevelius, for example, used techniques that mirrored printing processes of the era to create detailed lunar maps. His depictions unveiled the moon's topography, turning ethereal features into tangible, observable facts. It was a symbiosis of art and astronomy, where each stroke on paper brought the moon's surface closer down to Earth. Elsewhere, Cassini employed mathematical rigor in his observations from the Paris Observatory. The routine here was a balance of precise instrument calibration and celestial navigation. His calculations of lunar parallax were especially significant, refining the understanding of the moon's distance and its orbit, enhancing predictions of lunar and solar phenomena. In England, John Flamsteed followed the celestial rhythm from Greenwich Observatory. His routine was marked by patience and persistence, as he mapped the skies with unparalleled detail. Flamsteed's work contributed a wealth of star data that would support future generations and assist in nautical navigation. His methodologies in recording lunar phases were stringent, ensuring accuracy pivotal for the era's astronomical models. The rhythm of these routines was punctuated by moments of anticipation, particularly during eclipses. Edmund Halley, a keen observer of these rare events, worked tirelessly on predicting their occurrences with greater accuracy. He compared data across generations, refining calculations that detailed how the Earth's shadows played across the lunar surface, deepening humanity's understanding of these celestial spectacles. Across Europe, these daily lives weren't isolated endeavors. The astronomers existed in a connected network, sharing findings and techniques across countries. As night turned to day, letters carried observations and theories far afield, creating an unbroken chain of knowledge that transcended political divides. This interconnectedness enabled a broader scope of lunar understanding, cumulatively building towards greater astronomical insights. The golden age of astronomy did not halt at twilight's end. These astronomers succeeded in laying down the groundwork for modern lunar science, their routines intertwining with each new phase of the moon. Their diligent work, absorbed in nightly rituals beneath the moon's steady glow, was shaping the eras to come. As the chapter closes, imagine the quiet satisfaction felt by these early astronomers as their well-worn paths left imprints upon the global understanding. This daily life, marked by rigorous study and continual innovation, encapsulated the essence of discovery. With each cycle of the moon, they painted a clearer picture of its mysteries, setting the suspension of night into a grand narrative of exploration. In the serene embrace of the 19th century's twilight, astronomers embarked on a new era, one where lunar exploration would be transformed by emerging technologies and instruments. These innovations were driven by a relentless pursuit of clarity, as they strove to peel away the shroud that obscured the moon's secrets. This chapter delves into the advanced instrumentation that redefined the pursuit of lunar observation. The journey into advanced lunar observation technology began with the advent of photography. In 1839, the daguerreotype was introduced, offering the first opportunity to capture images of the moon through a camera lens. This method significantly enhanced the accuracy of lunar maps by allowing astronomers to record visual data directly. John William Draper, an American scientist, successfully captured the first known photograph of the moon in 1840. His work marked a pivotal shift, transforming sketch artists into photographers armed with this powerful new tool. Throughout the mid-19th century, improvements in telescope optics made substantial strides. Reflecting telescopes, first conceived by Isaac Newton centuries earlier, advanced significantly in this era, enabling astronomers to achieve higher resolution images. The use of larger mirrors and sophisticated mounting systems allowed observers to stabilize and focus on celestial objects with unprecedented precision. One of the most notable of these was the Leviathan of Parsonstown, created by William Parsons, the 3rd Earl of Ross, in Ireland in 1845. At 6 feet in diameter, it provided some of the clearest images of the mid-century moon, underlining the correlation between mirror size and resolution. Furthering precision, spectrometry emerged as a crucial tool in lunar observation. By analyzing light spectra, astronomers like George Biddell Airy, the Astronomer Royal, sought to understand the materials composing the moon. This technique measured the wavelengths of light reflected from the moon's surface, offering new insight into its physical characteristics, a leap from mere visual interpretation to scientific inquiry regarding its composition. In the late 1800s, timing technology also revolutionized observation methods. The introduction of precise clocks and chronometers refined the temporal resolution of astronomical measurements. This advancement allowed for accurate tracking of lunar phases, eclipses, and transits, essential for scientific experiments requiring strict timing, such as observing lunar eclipses to test gravitational theories proposed by physicists like Isaac Newton and Galileo before them. By the 1880s, electrical technology ushered in further sophistication. Developments in signal transmission meant observations could be communicated almost instantaneously over long distances, a true revolution in international collaboration. Instruments like chronographic recorders could document astronomical phenomena with accuracy, timing observations to fractions of a second. No longer bound by manual recording alone, astronomers integrated electrical methods, enhancing the efficiency and accuracy of data gathering. Refractors, the telescopic style using lenses to form images, witness a resurgence in this period as well. Instruments such as the Great Refractor at the Lick Observatory, completed in 1888 with its 36-inch objective lens, pushed boundaries in lunar photography and observation. This telescope offered unprecedented detail, further encouraging observations into our contiguous celestial neighbor. In summary, instrument innovations in the 19th century transformed the scope and detail of lunar observations. The marriage of new technologies with established astronomical techniques enabled a greater understanding of the moon's nature and composition. Long after the sun set on this era, the methodologies developed continued to illuminate and inspire modern lunar exploration. These pioneering tools and technologies set the stage for a future where the moon would continue to intrigue and perplex humanity, a testament to our enduring quest to understand the universe beyond our earthly bounds. As the 19th century unfolded, new scientific advancements became bridges to understanding the moon's mysteries. A major leap forward during this period involved the use of improved telescopes and photography, transforming how astronomers studied the lunar surface. Not only did these developments allow for better observations, but they also sparked further discoveries about the moon's nature and structures. Photography emerged as a groundbreaking tool for astronomers. In 1840, American scientist John William Draper captured one of the earliest known photographs of the moon, significantly improving the way lunar features were documented. This invention enabled astronomers to preserve exact visual data rather than rely solely on hand-drawn sketches. As photography advanced, so too did the quality and detail of lunar maps, providing richer and more precise topographical information. Simultaneously, advancements in telescope design revolutionized lunar observations. Reflecting telescopes, initially conceptualized by Isaac Newton, saw significant improvements during this period. By increasing the size of mirrors and enhancing their mounting systems, astronomers could achieve clearer, more detailed images of the moon. The Leviathan of Parsonstown, created by the 3rd Earl of Ross, William Parsons, in 1845, epitomized this era's advancements. With its 6-foot diameter mirror, the Leviathan became the most powerful telescope of its time, offering unprecedented clarity of lunar imagery. Incorporating these technologies, astronomers could explore the moon's surface in unmatched detail. The reflective techniques used in these telescopes allowed scientists to study the rugged topography of the moon. Craters, mountains, and vast plains were now subjects of careful analysis, presenting the lunar landscape as more diverse and complex than previously imagined. Another significant breakthrough came from the field of spectrometry. By the 19th century, this technique allowed the analysis of light spectra to determine the moon's composition. Astronomers discovered that the colors of light reflected from the moon could reveal what elements were present on its surface. This was a considerable shift from mere visual observations to analyzing the moon's makeup, focusing scientific inquiries on what the moon's geological history might be and setting a precedent for future studies. In addition to these optical and analytical technologies, the precision of timekeeping played a vital role in lunar exploration. Electrical timing devices refined the measurement of celestial phenomena. By the 1880s, these advancements allowed astronomers to track lunar phases and eclipses with incredible accuracy. Instruments like chronographs could time events down to fractions of a second, providing new insights into the synchronization between lunar motions and earthly observations. These improvements in timing were critical for testing theoretical predictions and further understanding the gravitational influences between Earth and its closest celestial neighbor. Such exactness also facilitated international collaborations, as observations could be reliably shared and compared across the globe. Thus, as the 19th century drew to a close, the innovations in lunar observations became a testament to human ingenuity and the capacity to deepen our understanding of the natural world through technology. The era set the stage for an ongoing inquiry, pushing the boundaries of knowledge and igniting a continued quest to unlock the moon's lingering enigmas. As the night sky unfolded, humanity carried forward its legacy of looking up, equipped with ever more refined tools to connect our earthly existence with the cosmic stories written in the stars above. In the mid-20th century, the drive to explore uncharted territories shifted dramatically and pointed toward the dusty plains and shadowed craters of the moon. These ambitious voyages and expeditions were driven by a quest to understand the mysterious lunar surface more intimately than ever before, setting human eyes on locations previously seen only through telescopic lenses and photographic plates. It was during the height of the Cold War that this ambition took a giant leap forward. The space race between the United States and the Soviet Union became a key battleground. In October 1957, the Soviets launched Sputnik, the first artificial satellite, igniting a surge of space exploration efforts worldwide. This launch marked the beginning of an era where reaching the moon was not just a dream, but a national effort, symbolizing technological prowess and advancing scientific discovery. By 1959, the Soviet Luna program had already achieved significant milestones. Luna 2 became the first human-made object to reach the moon, impacting in September of that year. This was immediately followed by Luna 3, which successfully photographed the far side of the moon, revealing landscapes never before seen by human eyes. These early Soviet missions paved the path for more complex explorations, marking a significant achievement in space exploration technology. Meanwhile, the United States ramped up its efforts with Project Mercury, creating a foundation for human spaceflight. In 1961, President John F. Kennedy famously committed America to landing a man on the moon before the end of the decade, setting in motion NASA's Apollo program. Apollo represented the pinnacle of human ingenuity matched against the vastness of space, a monumental effort involving thousands of scientists, engineers, and astronauts. As NASA worked toward this goal, uncrewed missions provided invaluable information. The Ranger program saw several probes sent to crash land on the moon, transmitting photographs back to Earth up until the moment of impact. This data was essential for identifying potential landing sites. The Surveyor program further contributed by achieving soft landings, beginning with Surveyor 1 in 1966, sending back images and soil analysis, which confirmed the feasibility of manned landings. The climax of these efforts came on July 20, 1969, when Apollo 11 made history by landing humans on the moon. Astronauts Neil Armstrong and Edwin Buzz Aldrin became the first humans to walk on the lunar surface, leaving footprints in the powdery soil and collecting samples to bring back to Earth. Armstrong's famous words, "That's one small step for man, one giant leap for mankind," etched the event into the collective memory of people across the globe. Apollo missions continued until December 1972, with each mission enhancing scientific understanding. Instruments were deployed to collect data on lunar seismic activity, heat flow, and magnetic fields. These missions expanded lunar cartography, creating detailed maps of its surface, while also painting a picture of the moon as a desolate yet scientifically rich environment. Throughout this exploration period, competition and collaboration pushed the boundaries of human achievement. The United States and the Soviet Union both made considerable contributions to the understanding of lunar phenomena. Their missions highlighted aspects of the moon's geology, revealing a complex history of volcanic activity and meteorite impacts. As these expeditions settled into history, they left a legacy of curiosity and exploration. The lunar expeditions became a testament to visionary thinking, showing how aspirations could be transformed into reality through innovative technology and international cooperation. Even as the last Apollo mission drew to a close, the lunar surface remained an intriguing subject, inviting questions and future exploration goals. Thus, the first human voyages to the moon transformed the world's understanding of our nearest neighbor in space. These expeditions showed that with curiosity, dedication, and technology, humanity could stretch the boundaries of possibility, stepping out into the vastness of space with determination and wonder. As the echoes of those steps faded, the knowledge they gathered continues to inform scientific inquiry, guiding the next steps in our cosmic journey. Amid the echoes of scientific progress, the 20th century introduced new challenges for lunar observation, deeply interwoven with the human conflicts of its time. The world wars and subsequent geopolitical tensions created both obstacles and surprising accelerators for those seeking to understand the moon. These conflicts reshaped priorities, funding, and international cooperation in ways that reshaped the very nature of astronomical exploration. Prior to World War I, astronomers had made considerable advances through observatories around the world. However, as nations became embroiled in conflict from 1914 to 1918, many scientific pursuits were hindered. Observatories in Europe found themselves crippled by resource shortages, and many scientists were diverted from academic research to military efforts. The war also disrupted international communication, a vital lifeline for scientists exchanging lunar data and insights. Yet, from adversity came innovation. The military need for improved optics and precision technology inadvertently benefited astronomical advancements. Precision lenses for gun sights and reconnaissance cameras led to better telescope lenses post-war. This intersection of military and scientific technology often resulted in more accurate equipment for observing the heavens, including our lunar partner. As the 1920s welcomed peace, yet under the shadow of diplomatic strain, international scientific collaboration was resurrected, if tentatively. The League of Nations fostered forums where scientists could again collaborate, leading to renewed efforts in lunar and astronomical studies despite underlying international tensions. This period also saw heightened emphasis on using balloons and high-altitude flights for better atmospheric observations, logistically born from aviation developments during the war. The approach of World War II once again placed observatories at risk. Scientists were conscripted into military service, and observatories near conflict zones became targets or were repurposed for military uses. However, the war also accelerated technological innovation, notably in radio wave technology and radar. Radar's role in wartime detection would profoundly influence later space-age innovations. Scientific minds conscripted for war efforts continued probes into the usefulness of radar, not just for terrestrial purposes, but in the grander cosmic theater. Post-World War II period ushered in the Cold War, marked by palpable tensions and fierce technological rivalry, notably the space race. Originating from the looming threat of nuclear warheads, rocket technology was initially military-driven, its aim redirected skyward toward peaceful space exploration ambitions. Investment in science and technology saw government budgets swell, notably in the US and USSR, directly benefiting lunar exploration capabilities. In the US, propelled by the Soviet launch of Sputnik, the establishment of NASA in 1958 signified a strategic pivot to space exploration, with significant focus on the Moon. Concurrently, the USSR's Lunar program fostered competition that accelerated technological growth. The Soviet Union's successful Lunar missions to photograph and land unmanned spacecraft on the Moon in the 1950s and 60s compelled the U.S. to grasp for the stars, ensuring continual investment and cooperative scientific pursuit in space technologies. Wars and conflict brought an ironic yet undeniable stimulus to lunar exploration through redirected resources and heightened competitive innovation. These conflicts crafted a landscape where governments recognized the Moon as a proving ground of technological prowess. Thus, through these trials, humanity paradoxically advanced its cosmic understanding. The chapter ends as it ponders the imprint of conflict on scientific advancement, noting the resilience and adaptability of astronomers and scientists who, despite geopolitical strife, continue to sow the seeds of lunar discovery, inspiring generations to probe further into the skies. As humans have pondered the mysteries above, the Moon has played a pivotal role not just in astronomy, but in shaping various cultures and scientific legacies throughout history. This celestial body captures our imagination with its gentle glow and steady rhythm, influencing societies in profound ways. Long before modern science took its grip, the Moon was already ingrained in human consciousness, a testament to its significant role in cultural beliefs worldwide. Many civilizations saw the Moon as a deity or an object of worship. In ancient Mesopotamia, for instance, the moon god Sin was an important figure, embodied in temple architecture and worship practices. These beliefs underpinned societal norms and served as guiding lights in times of uncertainty. In mythology, the Greeks spoke of Selene, the goddess of the moon, while the Romans equated her with Luna. These mythological narratives often intertwined with and informed the scientific inquiries of their time. They contributed to the cultural fabric, inspiring art, poetry, and philosophical debate. The moon's regularity and influence on tides and agricultural cycles granted it an essential role in the survival of early civilizations. Moving forward in time, the moon's pull reached beyond myth, bringing about a wave of scientific inquiry. This transformative phase began with detailed studies by early astronomers. By the age of the Renaissance, the narrative broadened. The moon became more than a cultural muse. It was a subject of rigorous observation and calculation. Luminaries like Johannes Kepler and his contemporaries elevated the moon from the backdrop of myth to a world of empirical study. The telescope's advent reshaped society's view of the moon entirely. Galileo's observations, revealing its mountainous terrain, challenged entrenched perceptions of celestial perfection. It marked a departure from classical assumptions, enabling a new lens through which to see our lunar neighbor, one governed by universal laws, not divine ones. In the Enlightenment period, lunar maps proliferated, and the moon became a centerpiece in the quest for scientific knowledge. The 17th and 18th centuries witnessed blossoming observatories dedicated to astronomical study, each contributing to a more profound understanding of the moon's physical characteristics and motion. The moon also left an indelible mark on the arts and literature. It served as a muse for poets like Lord Byron and Shelley, who, inspired by its ethereal presence, explored profound themes of nature and existence in their works. Artists often depicted it as a symbol of beauty and mystery, its serene silhouette providing a backdrop to countless masterpieces across eras. In more modern times, the moon influenced our aspirations beyond Earth. It was symbolic of discovery during the space race, a global contest infused with pride and geopolitical ambition. As the United States and the Soviet Union vied for space superiority, the moon became the ultimate prize, embodying the pinnacle of human achievement and technological prowess. With the success of missions such as Apollo 11, which saw humans set foot on the lunar surface, the moon transitioned from a distant icon to a tangible world of exploration. These missions piqued global curiosity and inspired generations to look beyond our planet for answers to fundamental questions about life and the universe. Today, the moon's allure remains undiminished. While we continue to explore its surface through rovers and advanced telescopes, its cultural and scientific legacies persist. It continues to captivate as both a symbol of human curiosity and a reminder of our collective past and aspirations. As we gaze upward, the moon stands as a constant fixture in our night sky, a witness to the history we've carved out beneath its watchful eye, guiding us toward a future as expansive as the universe itself. This ongoing legacy of exploration and connectivity to our celestial companion lays a foundation for what comes next in humanity's enduring journey to understand our place among the stars. In the twilight of astronomy's storied past, the closing days of many lunar observatories were marked by a gradual decline, an echo of their once resounding influence. By the mid to late 20th century, several long-standing observatories faced operational challenges. Shifts in scientific priorities, funding shortages, and advancements in technology led to a decline in the roles these scientific bastions had played for centuries. The landscape of celestial observation, which had once centered on grand observatory towers, began transforming. One of the key reasons for this evolution was the emergence of new technologies. As radio telescopes and space-based observation platforms like satellites started to provide clearer and broader views of celestial bodies, the need for traditional ground-based observatories diminished. These advanced instruments overcame atmospheric distortions that hampered terrestrial observations, furnishing astronomers with the capability to obtain unprecedented data from outer space. This transitioned focus from optical telescopes to more innovative approaches ultimately meant that some historic observatories struggled to maintain relevance in an era driven by technological leaps. Moreover, economic factors weighed heavily on these institutions. For many, maintaining operational status became increasingly difficult without sufficient funding. The resources needed to keep aging equipment functional, alongside the modernization necessary to stay competitive, proved challenging. As investments in space exploration soared, traditional observatories often found themselves sidelined. Initiatives such as NASA's Hubble Space Telescope project, launched in 1990, embodied a transition toward funding cutting-edge space missions over terrestrial observatory upkeep. The human element also played a role in the decline. Many senior astronomers who had operated these revered observatories retired, and younger scientists gravitated towards novel research areas and cutting-edge technologies. This shift in talent and expertise away from traditional observatories meant that fewer people were available to manage them, contributing to their slow descent into obsolescence. Despite these challenges, it is important to remember that the legacy and data from these institutions served as a foundation for contemporary research and exploration. Additionally, the preservation of historical observatories as cultural landmarks and museums became a vital mission for those who understood their cultural and scientific importance. Observatories like the Lick Observatory in California found new life as centers for public education and outreach. They became places where the history of astronomical discovery met public curiosity, rekindling wonder about the cosmos in the minds of regular visitors. This transition often mirrored a broader trend within scientific history, where each generation builds upon the achievements of its predecessors, sometimes moving beyond older methods to embrace innovation. As the capacities to look further and in greater detail emerged, former observatories were often refurbished into educational sites, bringing the past and present together under one roof. These settings had the unique ability to bridge history with modern technology, preserving insights from the past while inspiring future astronomers and scientists. Significantly, some observatories managed to reimagine their roles. With revitalization efforts and upgrades, they housed community-oriented programs, skywatching events, and astronomy nights, inviting the public to engage with the stars. This redefined their purpose, from being merely observational facilities to becoming venues for participation, education, and awareness. The bond once formed between observers and the grand devices they commanded evolved into a wider, more accessible relationship between human invention and celestial allure. As attention turned to the skies within the framework of groundbreaking technologies, the story of these observatories also unveiled the continuity of human curiosity. Although some structures fell silent, others regained their voice, speaking now to new generations. On these towers of exploration, the final chapters may have written themselves, but the impact of their insights, views of the moon's craggy surfaces, stories engraved within the telescopes, continue to shape the stories modern science tells. In conclusion, the shift from operational stardom to quieter roles may have spelled a kind of closure for many cherished observatories. Yet, it also penned a new chapter, a tribute to both discovery and community, bound together by a shared quest for understanding. As one looks forward to an ever-unveiling cosmos, these ancient stones remind us of human endeavor's persistent glow, a testament to reaching beyond what once seemed unreachable. In the tranquil corners of our planet, scattered like forgotten gems, lie the remnants of once proud observatories. These silent sentinels, once at the forefront of celestial discovery, now stand as echoes of an era where humankind sought answers by peering through powerful lenses to map the vastness of the night sky. While many have receded into obscurity, their walls still whisper stories of exploration and the unyielding quest for knowledge. As technology evolved past the traditional optical telescopes, many of these observatories faced relegation due to the rapid advancements in space-based exploration and the rise of radio telescopes, which provided clearer and broader data from the heavens. Despite these changes, the contemporary relevance of these historical sites persists in ways both humble and grand. Today, these observatories represent more than just venues of scientific inquiry. They are cultural landmarks and educational bastions bridging past and present. A visit to one such relic can transform ordinary curiosity into profound understanding. Take, for example, the Griffith Observatory in Los Angeles. While still operational to an extent, it has become an educational hub open to the public, hosting events that merge science fiction with science fact. Its programs invite audiences to gaze at the universe through its historic Zeiss telescope or participate in interactive exhibits that explicate the cosmos. These observatories offer an immersive journey back in time, where visitors can retrace the footsteps of astronomers who contributed to pivotal discoveries in lunar mapping and measurement. At many sites, the architecture of domes and towers, crafted from stone and steel, stand as a testament to past human endeavor. Observatories like the Lowell Observatory in Arizona, once a pivotal center in lunar research, now serve as vibrant educational centers. They entice amateur astronomers with public viewings and teach visitors about the history of astronomy and the ongoing quest to decode the secrets of our moon and further celestial wonders. The transformation of these observatories into cultural landmarks underscores their ongoing importance. Reimagined as historic sites open to the public, they preserve not only instruments and artifacts from their operational past, but also the narratives of the scientists who labored beneath the stars. Emphasis on the educational value of these structures draws new generations into the wonders of astronomy, an effort to spark the same fascination that propelled early astronomers to gaze upwards. In Europe, the Royal Greenwich Observatory, a bastion of astronomical history, has transitioned from pure research to a part of the National Maritime Museum in London. It attracts thousands annually who come to stand on the prime meridian, an enduring symbol of navigational science anchored by lunar observations. These places weave scientific history with educational outreach, encapsulating centuries of celestial study in ways that illuminate today's astronomical pursuits, and in turn, inspire countless learners and future scientists. Similarly, the Astronomical Observatory in Paris now highlights its historical achievements through tours that feature the instruments used in pioneering lunar studies, the same equipment that drove early astronomical photography in the 19th century. By understanding their role in history, one appreciates how these relics inform the continuously unfolding narrative of our exploration of the universe. Though these observatories may have largely ceded their research roles to advanced space stations and remote telescopes, their lasting contributions and inspirational influence remain undiminished. Through a shift toward educational and cultural roles, they preserve a lineage of human inquiry that transcends generations. Even as modern technology shifts the epicenter of astronomical observation into space, the essential foundation laid by these distinguished sites continues to support them. In the shadow of these storied constructions, both casual visitors and committed astronomers find a shared vista, a bridge between the tangible history of lunar exploration and the uncharted possibilities that lie ahead. This juxtaposition of heritage and forward-looking exploration leads us into a new age where innovation and inspiration coexist, bound by humanity's timeless desire to understand the moon and the heavens beyond. The pursuit of preserving the historical footprint of lunar exploration is an enduring endeavor, ensuring that the legacy of our celestial past remains safeguarded for future generations. This chapter explores the various efforts to preserve and commemorate the valuable scientific contributions made by historical lunar observatories and missions. As scientific discoveries continue to evolve, the need to conserve the sites and artifacts that embody our lunar journey has become increasingly important. In recent years, initiatives have sprouted globally to protect these vital pieces of history. Observatories are recognized not only as architectural landmarks, but also as symbols of human curiosity and the quest for knowledge. One significant effort includes the UNESCO World Heritage Sites designation, which identifies and maintains observatories with notable contributions to lunar and astronomical sciences. A primary example is the preservation of the Jantar Mantar in India, a collection of 18th-century astronomical instruments. Recognized for its architectural and scientific importance, it serves as a testament to ancient lunar observations. Despite the evolution of modern instruments, efforts such as these underscore the value in maintaining physical connections to the historical methodologies that shaped our understanding of the Moon. The transformation of historical observatories into museums has become a common approach. This practice enables public engagement and education about the essential role these sites played in astronomical advancement. The Palomar Observatory, for example, has transitioned partly into an educational center where visitors can learn about its groundbreaking lunar findings. These museums emphasize interactive displays and guided tours, bridging past discoveries with young learners and curious minds eager to understand the scope of lunar exploration. The preservation of lunar landing sites has also been a topic of discussion among historians and scientists. The Apollo landing sites are recognized not just as locations of historical achievement, but as places deserving protection for their cultural significance. Various organizations advocate for legally safeguarding these areas, proposing international treaties to ensure their conservation, much like terrestrial heritage sites. Restoration projects have also taken priority, where astronomical instruments and observatories are meticulously maintained and repaired to adhere to their original functional state. The aim is not only to preserve the instrument for historical observation, but also to inspire hands-on learning activities that depict how astronomers collected lunar data in the past. Aside from physical preservation, digital archival projects have emerged as significant endeavors for maintaining the narrative of lunar exploration. Comprehensive digital archives, like those from NASA's Apollo missions, ensure that primary data, images, and communications are accessible for educational and research purposes. Digitization allows for the protection of fragile documents while making them available to a global audience. Education plays a vital role in these preservation efforts. Academic institutions and observatories often conduct workshops that delve into the history of lunar studies. By engaging with students and communities, these programs ensure that the historical significance is not lost, but rather embedded into the learning experiences of new generations. As these initiatives cast their gaze towards safeguarding the lunar legacy, they foster a deeper understanding of the advancements built upon today. Each effort to restore and remember brings with it a recognition of the tireless work of those who turned lunar mysteries into scientific principles we uphold. These initiatives symbolize an acknowledgement that our journey toward understanding the Moon and the cosmos is woven into the broader tapestry of human history. Looking forward, it is vital that these preservation efforts continue to evolve, ensuring that as we venture further into space, we do so with a rich appreciation of the paths that led us here. The Moon's enduring enigma serves as a reminder of the creativity and persistence of humanity, echoing across time and inspiring new generations to look up and ask anew, what lies beyond? Throughout history, our exploration of the moon has left a rich legacy, underscoring the profound impact that forgotten observatories have had on our understanding. Not only did these observatories serve as beacons of scientific discovery, but they also laid the groundwork for the insights we rely on today. Their contributions form a silent, yet potent legacy, one that continues to shape and inform our modern approach to lunar and astronomical study. These observatories, established from the Gothic Revival period through to the brink of the 20th century, were critical in transforming lunar observation. They provided the precise calculations and detailed observations necessary for the development of accurate lunar maps and theories. They also laid the foundation for understanding the moon's cycles and established the groundwork for future lunar missions. Significant figures like Galileo, Hevelius, and Cassini found within these observatories the tools and environment necessary to push the boundaries of what was known about the moon. The twilight of these forgotten observatories did not signify the end of their influence. Their historical work continues to resonate throughout the scientific community, forging a path for the development of advanced technologies and methods. Even as we shifted from optical methods, the records and data preserved from these observatories provided a base from which modern lunar mapping and exploration have expanded. This era illustrated the transformative power of collaboration and meticulous observation, as scientists across the globe shared insights and techniques. With the advent of radio telescopes and, eventually, space telescopes, the landscape of astronomical observation has evolved in ways the original builders of these observatories could scarcely have imagined. Yet, the foundational knowledge and methodologies cultivated within these observatories have persisted. From tracking the moon's parallax to predicting eclipses, these traditional methods remain essential in the arsenal of modern astronomy. Furthermore, the legacy of these observatories has inspired current educational endeavors. They serve as a reminder of the importance of maintaining an inquisitive perspective towards our celestial neighbor. Many have been transformed into interactive museums, highlighting the historical significance and inspiring new generations of astronomers and scientists. This reflective journey through history underscores a crucial point. The scientific achievements of the past continue to inform the present. The observations and insights gleaned from these once bustling centers of learning have quietly but enduringly permeated modern scientific inquiry. As we look to the future of lunar research and exploration, we do so standing on the shoulders of these early efforts, proof of humanity's unwavering quest to understand our universe. Our current endeavors, from planned lunar missions to ongoing robotic exploration, benefit enormously from the groundwork laid by these observatories. The meticulous record-keeping, the dedication to night-after-night observations, and the desire to connect the unknown with the known propel our continued journey forward. As our gaze turns once again to the moon, we carry forth the silent legacy of these observatories, using shared knowledge to reach new heights in understanding an ancient celestial wonder.